So what we do in this section is we add and subtract. First we add and subtract, and then we get into the part which is really the title of this lesson, which at least as far as the textbook goes, which they call binomial radical expressions, which will involve some kind of dividing. Okay, so that's why the second objective, which comes from the SRLs, is somewhat true. So let's remember, for adding and subtracting radicals, that a radical has an index. That's the number in the hook, right? It has the radical sign, and it's got whatever's inside the radical, which we call the radicand. You can only add or subtract radicals if they have the same index and the same radicand. They have to be the same, right? If they have the same index and the same radicand, they're called like radicals. It's like when we say combine like terms, same intent there. Like radicals. Like terms you can add together. Like radicals you can add together. So these are called like radicals. Get it over with. Come on, hurry up. Ready? Right, if you're going to take notes, the second the slide gets up there, start taking notes. Don't wait till I've already talked the whole thing and then you're going to start taking notes, because I'm going to move on. You can download these if you really want them. Okay, most of it's just copied right out of your book. Okay, so let's see. This is how they describe, right, the adding or subtracting of radicals, the combining. Right, as long as they have the same index and the same thing inside, the way you combine them is by combining the coefficients. Right? Now, if you look at it on top, I mean, everything's in terms of x's and n's and a's and b's and all this. If you look at it here in the example, maybe it makes more sense. Right? The square root of 5x, the square root of 5x, those are like radicals, because what's the index of both of them? 2. Right? And what's the radicand? 5x. So they have the same index, the same radicand, therefore you can add them. Or in this case, subtract them. How are you going to do that? By combining the coefficients, 3 minus 2, like this. Right, that becomes 3 minus 2 times the square root of 5x. I mean, they call it distributive property. Honestly, they should call it factoring. That's really what we did. There was a square root of 5x in both terms, so we factored it out. And what was left behind was 3 minus 2. And 3 minus 2 is a simple, that's just the square root of 5x. Okay. How about this one? Can we add them? Cannot add them because which is not the same. Okay, the index is the same. It's the square root and the square root. But the radicand, in this case, it's 7. In this case, it's 5. So they're not like radicals. So you cannot add them. Right? So you don't. You cannot combine these expressions. How about this one? Can you combine them? No, because what's different this time? The indexes aren't the same, right? One's a third root and one's a fifth root, so you can't combine them. How about, there's 3 on the top there. Which one of them can't you add? The first one, because what is it that's different? The index is not the same, right? So this one, oops, right, can't combine. How about the next one? Are they the same? Are they like radicals? Yeah, okay, they're like radicals, so how do you combine them? You add the coefficients. The coefficients are 3x and 4x, right? That's 3x plus 4x times the square root of xy. And 3x plus 4x is 7x. How about the last one? Are they like radicals? Sure, they're like radicals. They are the 5th roots of 3x squared, right? So how do we combine them? 17 minus 15, right? So we just combine those two, we get 2 times the 5th root of 3x squared. Easy stuff, right? Try that one. Are they like radicals? No. See, you might look at that and say, they're not like radicals, can't add them, I'm done. But if they can be simplified, you need to simplify them, because maybe after you simplify them, they are like radicals. So don't say you can't simplify them if you actually haven't tried to simplify them first. For example, the square root of 12, simplify it. 12 is not a perfect square, but what is the factor of 12 that is a perfect square? 4, right? So we're going to write this as 4 times 3. Okay, 75 is not a perfect square, but does it have a factor that's a perfect square? 25, right? So that would be 25 times 3. Square root, there's a plus in between. And the last one is just the square root of 3 anyways. So now let's simplify left to right. That's 2 times the square root of 3 plus 5 times the square root of 3 minus the square root of 3. Now are they like radicals? Yeah, they're all the square roots of 3. So now you combine them by combining the coefficients, which gives you what? 2 plus 5 minus 1. Right? If you see a radical there, then it's there once. So how many is that? 2 plus 5 minus 1 times the square root of 3, which is 6 times the square root of 3. Good. Jessica? Okay. Okay, these are cube roots. Again, they don't look like they are like radicals, but they could be simplified. You know, 250 is not a perfect cube, but what's a factor of 250? That is a perfect cube. Yeah. Remember, you check your list. There's your list of the perfect cubes right there. Right? 125 times 2, 250. So that's the one you want. And the 54 is not a perfect cube, but what's a factor of 54 that is? I mean, at this point, you should be thinking, what do you get if you divide 54 by 2? 27. Is 27 a perfect cube? Yeah, that's it. So 27 times 2. And how about 16? Is 16 a perfect cube? No. Does it have a factor that's a perfect cube? 8. Right? 4 is not a perfect cube. So we have the third root of 125 times the third root of 2 plus the third root of 54 times the third root of 2 minus the third root of 8 times the third root of 2. So that is 5 times the third root of 2 plus 3 times the third root of 2 minus 2 times the third root of 2. Now are they like radicals? All right. How many third roots of 2 do you have? 5 plus 3 minus 2. 6, right? So that is 6 times the third root of 2. Right? And don't change them, right? When you're putting these together, don't think that like makes it the third root of 2 squared or 2 to the third. You know, it's still, I always think of it like this, right? 5 oranges plus 3 oranges minus 2 oranges is 6 oranges. They're still oranges. They didn't change the basic nature of the thing you were adding and subtracting, right? Don't change those. So try that one. How do you simplify the square root of 20? 4 times 5, right? And how did you simplify the square root of 125? 25 times 5, right? So that is, so we have 14, which is on the outside, times the square root of 4, times the square root of 5, minus 3, which is on the outside, times the square root of 25, times the square root of 5. Simplify. 14 times 2 times the square root of 5, minus 3 times 5 times the square root of 5, which is 28 times the square root of 5 minus 15 times the square root of 5. How many square roots of 5 are there? 13. 28 minus 15. Okay. Okay, now we get into the part which is why this thing is called binomial radical expressions. Right? Binomial radical expressions, you know, basically, you know all the parts of that. Binomial means 2 terms, right? Radical means includes a radical in there somewhere, right? Examples would be something like this. 1 plus the square root of 2, right? That's 2 terms, and there's a square root of 2 in it, right? The square root of 3 minus 4. 2 terms, it's got a radical. You could even have two radicals, right? 5 times the square root of 6 plus 7 times the square root of 8. Two terms, both have radicals in them. That's what we mean by binomial radical expressions. Good, good, good. All right, so now we're going to multiply binomial radical expressions. Now, how do we normally multiply binomials? When you multiply two things times two things, what's our normal process we call it? We call it FOIL, right? So we're going to FOIL. This is just rewritten. The problem is just rewritten here, right? So we're going to FOIL these two terms times these two terms. All right, so here's multiplying the first. 4 times 5, there you go. Then you've got 4 times 4 root 2. Right. Then we've got 5 times 2 root 2. And then you've got the 2 root 2 times the 4 root 2. Now let's see which things are going to simplify. The 4 times 5, 20, right? How about the 4 times 4 root 2? 4 times 4 root 2. 16 root 2, right? And the 2 root 2 times 5. 10 root 2, right? And then at the end, you're going to have 2 times 4, which is 8. And what's the square root of 2 times the square root of 2? 2, right? I mean, you got to have, that needs to be like this. I mean, we did that even in what we were doing last night in the homework. You know, whenever you multiply the square, oops, get that back where it was. Whenever you multiply, right, the square root, a square root times a square root, it's like saying the square root of 5 squared. So it's just 5, right? And that's, you know, however many times you want to do that. The square root of x times the square root of x, x. So in this case, right, so they simplified along the lines of what we did. Maybe they didn't explain the last one very well, right? The 2 times 4 was 8. 8 times 2 is 16. Okay, now you can simplify, right? You've got two radicals in there. 16 root 2 plus 10 root 2. Those are like radicals. So how many root 2's are there? 26. And then you've still got the numbers that don't include radicals, 20 plus 16. Right? So there's your 36. 20 plus 16 is 36. 16 root 2 plus 10 root 2, 26 root 2. So they had to show us how you add and subtract radicals so that we'd be able to do this kind of thing. Okay, 3 minus. So let's do another. What is the product? Right, you're going to FOIL it. 3 times 5. 3 times the square root of 7. Negative square root of 7 times 5. And negative square root of 7 times square root of 7. The square root of 7 times square root of 7 is 7. And then the minus times a plus makes, well, they didn't even show that yet. Right, so there's the 3 times 5 is 15. We had the like terms, 3 root 7 minus 5 root 7, negative 2 root 7. And then again, this one, the square root of 7 times the square root of 7 is 7. Now, one last bit of simplifying. 15 minus 7 is 8. Right? When we're doing work with this, you can't just like put it in your calculator and turn them all into decimal. You're going to get no credit for that at all. You expect to see unresolved square roots, things that can't be simplified, but they're still square roots. So try that one. Try to FOIL that one and see what you get. Rebecca, right, head up. Who's got an answer? Lee? Let's see. I'm going to check you against this. Exactly right. Let's see. Do you have it? Where is it? It's correct. It's got 2 right answers. Who else got one? Curtis? Let's see. That's right. That's not right. Did you? What did you have? Nope. Well, the square root of 5 part is right. That's correct. The other 2 numbers are not. Go back, check your work. That part is right. That part is not right. Right? FOIL. FOIL. First terms. Right? The first terms, 3 times 2, 6. Then outer terms, 3 times 4, root 5. What is that? 12 root 5. Right? The inner terms, 2 times 2 root 5 plus 4 times the square root of 5. And then the last ones, right? 2 times 4 is 8, right? And the square root of 5 times the square root of 5 is 5, right? So this is 6 plus 16 root 5 plus 40, which is 46 plus 16 root 5. Okay. So we're almost done, are we? Where's all the slides coming from? Maybe not. Good. Okay. Right. Now let's do this one, right? FOIL. 5 times 5, 25. Okay. 5 times the square root of 7. 5 times the square root of 7, right? How about 5 times negative square root of 7? Minus 5 times the square root of 7. And then minus the square root of 7 times the square root of 7 is minus 7. Okay, so this, now we can, the 25 minus 7 is 18. The 5 root 7 minus 5 root 7 cancel each other out. So the answer is 18. So did you notice anything similar between the two factors? Yeah, one's a minus and one's a plus, right? It's called conjugates. When the only thing that's different in between them is the sign in between. Those are called conjugates. I believe we did this in when we dealt with imaginary numbers. We learned that if the only thing different is the sign in between, then those were complex conjugates. But even if it doesn't have an I in it, it's still conjugates. If the only, I mean, you could write this like this: 5 plus or minus the square root of 7. And what does that look like? Something coming out of the quadratic formula, right? That's generally where you get that kind of a thing. Okay, whenever you multiply conjugates, binomial radical expressions, which are conjugates, always all of the radicals will cancel, right? When you multiply conjugates, here those two canceled, and these, when you multiply, that got rid of the radical too, and that'll always be the case, right? So when you multiply binomial radical expressions, which are conjugates, and I'm just going to say A plus or minus the square root of B. All radicals cancel. Okay, so let's see. If I'm going to FOIL these two, right, then again, I can FOIL. I'm going to come up with 4 terms, right? The first terms are 36 plus 6 root 12 minus 6 root 12 minus 12. And the middle 2 terms cancel, right? And they always will. So the thing is, when you're doing FOIL, do you really need to do the middle 2 terms? No. Normally you won't. Like in the second one here, let's not even bother with the middle 2 terms. We know they're going to cancel, right? That'll be 3 times 3 is 9, minus 8, which is 1. I just didn't even bother making the last, the middle 2 terms, because they're going to cancel. They always do. Right? This one would have been 24. So knowing that, that helps us when we want to rationalize the denominator, which includes a binomial radical expression. What will we multiply by? The conjugate. That'll get rid of all the radicals. That'll turn an irrational number into a rational number. Remember, we did this last time, right? This is the same slide from last time. We said if solving a right triangle, which is 45, 45, 90, we would say if x root 2 equals 5, then x equals 5 over the square root of 2. And then the strategy for getting rid of that square root in the denominator was multiply by the square root of 2 over the square root of 2, right? And that gave us 5 root 2 over 2. Right? That's one kind of rationalizing denominators. Right? And then we did this one. I shouldn't even have copied that slide. But again, what would I have multiplied this one by to rationalize the denominator? The square root of 8x over the square root of 8x. Okay. For binomial denominators, if I go through here, if I do this, right? If I multiply by 1 plus the square root of 3 over 1 plus the square root of 3, right? Then in the denominator, I'm going to have 1 plus the square root of 3 plus the square root of 3 plus 3, which will be 4 plus 2 times the square root of 3. So that didn't rationalize the denominator. I still got a square root. So this is not what you want to do. Don't multiply by the denominator. That's what you do when you just have one term. When you have two terms, you got to use the fact that when you multiply by conjugates, that rationalizes the denominator. So using the same problem here, what would I multiply by that would actually rationalize the denominator? 1 minus the square root of 3, right? 1 minus the square root of 3, 1 minus the square root of 3. Right. In the denominator now, because they're conjugates, it'll be 1 minus what? Remember, we're not doing the O and the I. We're just doing the first terms and the last terms. And the last terms are plus the square root of 3 times minus the square root of 3 minus 3. So by choosing the conjugate as the thing you multiply by, that rationalizes denominator. And in the numerator, we still have this 2 minus 2 times the square root of 3, which for this particular problem, right, is going to give us 2 minus 2 times the square root of 3 over negative 2. And then because you got 2's and everything, you can cancel that. Right, that'll be negative 1 plus the square root of 3. Right, multiplied by the conjugate of the denominator over itself. Okay, what would I multiply this one by? No. Say it again, Mark. What? What's the whole expression you're going to multiply? Yeah. Positive 3 times the square root of 3 plus 2. right? The conjugate does not change the sign of the first term. It only changes the sign in between the two, right? Just like in the quadratic formula, right? It's plus or minus in between them. That's the only thing that changes. So let's see. We want to multiply this one by 3 root 3 plus 2 divided by 3 root 3 plus 2, right? It's the conjugate of the denominator divided by itself. Right? In the numerator, that's going to give us 4 times 3, 12 times the square root of 3. 4 times 2 plus 8. Right? In the denominator, again, I don't need to multiply all 4 terms, right? Just the first terms and the last terms. Right? What is 3 root 3 times 3 root 3? 9 times 3, right? I mean, the 3 times 3, 3 root 3 times 3 root 3 is 9 times 3, right? These two give you the 9. These two give you the 3, which is 27. And then the negative 2 times positive 2 is minus 4. So now we've got 12 times the square root of 3 plus 8 divided by 23. Can I simplify anything there? What kind of number is 23? It's a prime number, right? So no, you're not going to have any common factors with 23. So you're done. I think there's one more for you to do, and then that's it. So try that one. What did you multiply by? 2 plus 2 times the square root of 8. Okay. Did you get some? Well, the negative 14 in the denominator is correct, but the numerator is not correct. You're going to have some radical in the numerator. It doesn't get rid of the radicals in the numerator. Right? Remember, you got to FOIL that. You got to use this times this times this. Yeah. Anybody get it? Come on, Lee. Is it? 6 plus 2. Which is that? 36. You have 6 plus 2 root 8? Yeah, that's not right. Let's do it. So the easy part is the denominator, right? Because those are conjugates. 2 times 2 is 4. And then what is 2 times the square root of 8 times 2 times the square root of 8? Right? That'll be 4 times 8, which is 32. So minus 32. Right? In the numerator, you got to FOIL it all. Right? 3 times 2 is 6. 3 times 2 square root of 8 is 6 times the square root of 8. 2 times the square root of 8 plus 2 times the square root of 8. And the last, the square root of 8 times 2 square root of 8. Yeah, the square root of 8 times the square root of 8 is 8 times 2 is 16. Okay, so let's see what simplifies here. The 6 plus, yes. Because the square root of 8 times the square root of 8 is 8. The 2 times 2 is 4. 4 times 8 is 32. Okay, so we have 22 plus 8 times the square root of 8 divided by negative 28. So first thing you could say, well, all those coefficients and terms are divisible by 2. So let's factor out a 2. That'll give us 11 plus 4 times the square root of 8 divided by negative 14. But that's not actually done either, because the square root of 8 could be simplified. What's that? Yeah, I mean, the square root of 8 could have been broken up into the square root of 4 times the square root of 2. That's 2 root 2. Right, so this one, I'll take it this way and say that's 11 plus 8 times the square root of 2 divided by negative 14.
Why did you go from 22 plus 8 to 8 instead of 11?
I divided out a 2. There's a factor of 2 in the numerator and a factor of 2 in the denominator, so I canceled it. Right? That cut all of these things in half. 22 became 11, 8 became 4, 28 became 14. And then I substituted for the square root of 8. That's 2 root 2. And that's how I got this right here. And that's the right answer. Okay, so we added and subtracted. We multiplied the binomial radical expressions so that we learned how to simplify or rationalize the denominators, which is a sense of kind of dividing. And those are the homeworks.